that M matrix, and look at the eigenvalue. If all eigenvalues are larger than 0, then M has to be positive definite. If any eigenvalue which is not larger than 0, which is equal to 0 or less than 0, then this matrix won't be positive anymore. This is if and only if. So if and only if. Okay, that's the property of that. So I'm just telling you how to do this. But to prove that, you may be able to look at the notes I put in the web in that of co-monumental matrix. Matrix. Okay. Well, I forgot one thing I haven't mentioned now. Let me mention to you this now. So if M larger than 0 and the damping matrix larger than 0 and K larger than 0, then the system is asymptotic. That means the eigenvalue, the real power eigenvalue, all negative. That means real part of eigenvalues, all real part of eigenvalues are negative. Right? So if M mass matrix positive matrix, damping matrix positive definite matrix, and stiffness matrix is positive definite, then the system is asymptotically stable. That means all the real parts of the system eigenvalue, I'm not talking about K eigenvalue, I'm not talking about Z eigenvalue, I'm not talking about M eigenvalue, I'm talking about system eigenvalues, all the real parts of system eigenvalue are less than 0. What do we system eigenvalue? The system eigenvalue means when we transform this second order matrix equation become first order. And that's first order equation that there's a matrix there. You can solve eigenvalue of that. So you don't have to solve eigenvalue. As soon as you conform this is positive definite, this conform this is positive definite, this conform that K positive definite, then the system has to be a stable system. You don't have to solve eigenvalue at all. I'm just giving you the idea. Okay. Now this is the property of this all positive definite matrix, because this property later on will be used for controller design. This concept will be used for control design. That's the concept. You got to be careful. All right. Now the matrix form of this. That's our TMB matrix form. We know that's the matrix form. Okay? And now we are going to look at this form. Move the M, the mass matrix here. We divided the whole equation by M1, 0, 0, M2 inverse. Then your formulation becomes this. So your M is gone now. All right? Then we define. Look at this, define. Define omega 1 square root K1 divided by M1. That means this is the system frequencies without T and B. All right? Now omega 2 equal to square root of K2 or M2. That's the frequencies for the TMD without system. Now, that's we are looking at the frequencies for two systems. One is for two physical systems. One is for physical system itself. One is for TMD. So this is the frequencies. And then we are going to define mu m equal to m2 divided by m1. And mu omega, see, I'm going to define this dimensionless. So this is dimensionless, right? M2 divided by M1, there's no dimension. Just like what I showed you in the video earlier. And then, but I define mu omega equal to omega 2 divided by omega 1 means I'm defining a parameter, dimensionless parameter. That's the ratio between the TMD frequencies and the system frequencies. Then I have a zone. I define equal to zeta 2. That's the best path coefficient divided by 2m2 omega 2, and this is all related to TMD parameters. All right. The reason I do this is one reason is to reduce the number of design parameters. Right? Because I can look at only mu, that's my design parameter. I can look at only mu, the omega, I look at this zone, and this is my design parameters. In theory, M1 is fixed because that's the system. K1 is fixed, that's the system. So in theory, we have M2, and we have zeta 2, we have a K2. That's my design, the design parameters. 3. Now I still have a 3 here, but however, I look at my M2 divided by M1 mu m. I look at the mu omega, that's omega 2 divided by omega 1, and I look at though. This is we call a damping ratio, right? That's the typical way to do it, and this is all dimensionless. It's all dimensionless. That means I don't have any unit for this. So if I don't have a unit for this, if I know those dimensional parameters, then I can come back to compute my M2. Come back my zeta 2 and come back my the other things. But after that, my equation of motion I can rewrite in terms of this looks more complicated, but you don't have any. You don't have. By the way, you don't really have any division here. Like M2 divided M2 divided M1 is all gone. So this is like. One, yeah, it's called parameterization's equation for second order. All right. So that is, if we do this, then you look at this and further simplify it, and then we have only omega 1 here. Other than that, omega 1 here. Other than that is all the dimensionless parameters, and except we have M1 here. The reason again I do this is so that when I design the system, DMD system, make it easier. That's the system, right? Oh, okay. Now let us look at the steady state response. Again, I'm not looking at the transient response. In here, I assume that the system initially at rest. Initially, the system doesn't move at all. Alright, so I'm looking at a steady state. Again, I'm only looking at steady state solution for this. Harmonic excitations. Be careful now. U1 equal to UT equal to U1 exponential I omega t. So exponential function is very it has been it's used in all the solution of the differential equations, but you have to be careful here. Now I'm going to show you why. Now I'm assuming that my U is harmonic excitation. Alright. Harmonic. What do you mean harmonic? Means either cosine or sine. That means harmonic. Okay.